Hi everyone, my name is David Wisth, and today I'll be presenting our ICRA paper entitled Preintegrated Velocity Bias Estimation to Overcome Contact Nonlinearities in Legged Robots. This research was conducted as part of the Dynamic Robot Systems Group at the University of Oxford. Accurate state estimation is a key enabler for dynamic locomotion of legged robots. And these legged robots have two main requirements for state estimation. The first is a high-frequency, locally accurate estimate that's mainly used for control purposes. The second is a lower frequency, lower drift estimate used for high-level tasks, such as motion planning or terrain mapping. Traditionally, legged robots have relied on kinematic inertial inputs for their state estimation. However, this tends to suffer from drift. As the robot walks, state estimators accumulate drift. The plot on the right shows the accumulated drift from two different kinematic inertial estimators. As the robot walks over different types of terrain with different gaits, the drift is approximately constant with the same conditions. One of the main reasons for this drift is that most kinematic inertial estimators assume rigid ground contact with white Gaussian noise. This enables the very simple measurement model that if the foot is in rigid contact with the ground, the velocity of the robot must be equal to the opposite of the foot velocity. However, this doesn't consider many real-life effects, including terrain deformation, slippage, and mechanical deformation of the robot. These extra effects are both challenging to model and observe. For example, how do you estimate and model the terrain properties of soft gravel? Previous approaches to dealing with contact nonlinearities, including dynamically varying the covariance based on probabilistic contact detection, or using hidden Markov models to better model the transition between slip and rigid contact states. On the other hand, in the mature field of visual inertial odometry, IMU bias estimation is standard, and there exist efficient methods to pre-integrate IMU measurements for use in factor graph optimization. We present a factor graph-based approach to state estimation that fuses visual, inertial, and kinematic measurements. Uniquely, we model contact nonlinearities, such as slippage and deformation, by estimating the kinematic velocity bias online. And we show through extensive experimental evaluation a 26% reduction in relative pose error compared to the baseline of no bias estimation. We implement our proposed method into our existing framework entitled VILENS, which stands for Visual Inertial Legged Navigation System. To give some context, I'll provide a brief system overview of the state estimation on the ANYmal robot. On the ANYmal robot, there is an existing kinematic inertial estimator that provides high-frequency state estimates to the controller. However, these state estimates suffer from drift. We augment this state estimation framework with a factor graph optimization that takes inputs from a separate IMU and stereo camera and produces lower frequency, lower drift state estimates. We aim to estimate the following state of the robot, which consists of the robot's base, orientation, position, and linear velocity, as well as bias terms. And these bias terms include the traditional IMU biases, as well as the proposed linear and angular velocity kinematic biases. We combine these measurements into a factor graph framework, which can also be expressed as an optimization problem, which includes costs from prior factors, IMU factors, stereo vision factors, and kinematic factors. As mentioned before, in traditional kinematic odometry, when the foot is assumed to be in rigid contact with the ground, the velocity of the robot is simply equal to the opposite of the foot velocity plus some angular velocity terms. To account for contact nonlinearities, we extend this measurement model with a slowly varying bias term. We then integrate these equations to come up with an efficient and incremental way to calculate pre-integrated twist factors. Now, it should be noted that For a particular gait and terrain type, the bias is approximately constant. As the gait or terrain changes, the bias will slowly adapt to the new optimal value. We evaluate the proposed approach on over 50 minutes of real-world outdoor experiments. These experiments were conducted at 2 locations, the first being the Fire Service College and the second being the Swiss Military Rescue Centre. For all experiments, we collect ground truth by tracking a reflective prism using a Leica laser tracker. This provides millimeter accurate ground truth for the entire trajectory within line of sight. Below is a comparison of the estimated and ground truth trajectory for the Fire College dataset. As you can see in this large dataset consisting of over 30 minutes of walking, the estimated trajectory tracks the ground truth quite well. We also show a 26% reduction in relative pose error compared to the baseline solution of integrating kinematics without bias estimation. An example of how bias estimation improves performance can be seen in this part of the Fire College dataset when the robot walks through a large puddle. As the robot walks through the puddle, the visual front end tracks features in the feature-rich puddle reflections, and this leads to a degradation in performance when using visual and inertial inputs only. However, by having an unbiased leg odometry input, we are able to reject these disturbances and greatly improve state estimation performance. An additional benefit of tightly coupling vision and leg odometry happens when leg odometry is compromised, such as when we apply external disturbances to the robot. In this case, even though the performance of the leg odometry is decreased, we can still robustly track the ground truth trajectory. As an example of how improving state estimation brings us towards our goal of dynamic robot locomotion, below is a video of the ANYmal robot performing perceptive locomotion using a terrain map generated with kinematic inertial estimates. As the state estimator drifts, the terrain map also drifts, leading to phantom obstacles. This actually causes the perceptive controller to fail even when walking on flat ground. In contrast, by using VILENS and the proposed pre-integrated twist factors with bias estimation, we're able to achieve lower drift state estimation. In turn, we can achieve lower drift in the terrain map and thus improve the performance of the perceptive controller. In conclusion, we've presented a visual inertial legged factor-graph state estimation system. We address contact nonlinearities, including slippage, terrain deformation, and mechanical deformation by estimating the kinematic bias online. We show that we can reduce the relative pose error by up to 26% compared to the naive integration of kinematics without bias estimation. Thank you very much for your attention, and feel free to contact me using the links below. Thank you.